Welcome students, in this class we will be learning the concept of reducible linear differential equations. So the form that we are looking is dy over dx positive p times y is equal to q times y raised to the power of n. Now this is the form we will be coming across, and we will have to convert this into dy over dx positive p times y is equal to q, where p comma q are functions of x. So this is what we are trying to achieve. Now let us just solve a question. So we given a problem, say solve x times dy over dx positive y is equal to x to the power of 3 times y raised to the power of 6. So this is the question we will be attempting to solve. So foremost, what I'm going to do is I'm going to take this as 1, and I'm going to be dividing. I don't want to have a coefficient here, dividing by x throughout. So when we do that, I would get dy over dx positive y over x is equal to, when I divide by x, this is going to be x squared times y raised to the power of 6. Now this is 2. Now what I'm going to do is I'm going to be dividing by y raised to the power of 6 throughout. So when we do that, this is going to be 1 over y raised to the power of 6 dy over dx positive. This is going to give me, because the y and y raised to the power of 6, they get cancelled, so this is going to be 1 over y raised to the power of 5 times x is equal to x squared. Of course y raised to the power of 6 goes away. Now I'm going to rewrite this as y raised to the power of negative 6 dy over dx positive y raised to the power of negative 5 divided by x is equal to x squared. So now I will take it as 3. Now I'm planning to make a substitution. So what is a substitution? This is a very important substitution. Okay, substitution. This is very important. So what I'm going to do is I'm going to say let z be equal to y raised to the power of 5. Then I'm going to be differentiating with respect to x. So when I do that, I get dz over dx is equal to negative 5 times y raised to the power of negative 6 times dy over dx. I can rewrite this, probably I can just keep it like this. So the substitution is, in place of dy over dx times y raised to the power of negative 6, which is present here, I have to substitute dz over dx. But the only thing is that I want to bring this 5 over here, and then I will have dy over dx times y raised to the power of negative 6. So this is a substitution that I would be making. So I can say, therefore, equation 3 can be rewritten as, in place of y raised to the power of 6 dy over dx, I would be substituting negative 1 over 5 times dz over dx positive y raised to the power of 5, that's going to be z times 1 over x is equal to x squared. Now I can get rid of this negative, 1 over 5, so I'm going to be multiplying by negative 5 throughout. So when I do that, this goes away, so I get dz over dx, so negative 5, so this is going to be positive of z times negative 5 over x is equal to negative 5 times x squared. Now this is typically of the form, this is of the form dy over dx positive p times y is equal to q, where p and q are functions of x. But only thing is that in place of y, I've got a z. So the general solution for this, so the solution, so what will be the state of the solution? We have already seen the solution for the differential equations of this fashion, right? But for this, the solution is going to be z times integrating factor is equal to integral q times, of course, integrating factor times dx, right? So positive constancy. So this is going to be the solution that we are trying to achieve. So now the integrating factor. So if is equal to e raised to the power of is actually integral p dx, right? So we will have to use this now. So clearly in place of the required y, or I would say the coefficient of p is going to be negative 5 times x times dx, which is equal to e raised to the power of negative 5 times integral dx over x, which is equal to e raised to the power of negative 5 times, this is ln x, which is equal to e raised to the power of ln of x to the power of negative 5. E and ln gets cancelled, giving me x raised to the power of negative 5. So this is my integrating factor. So now I need to consider integrating q. My q is negative 5 times x squared times e raised to the power of integral p dx. So that's going to be x raised to the power of negative 5 times dx. So this is what I've got. So if I were to push this down, this is going to be negative 5 times x squared divided by x raised to the power of 5 times dx, which is nothing but negative 5 times. This is x squared and x squared term gets cancelled. This will give me x power 3, but I need to integrate this, so I need to push this up in the numerator. So this is how I get it. But of course I don't have to do all these things. I could have got it here itself, but just for the sake of explanation I have brought this in this fashion. If I were to integrate this, I get x to the power of negative 3 positive 1 divided by negative 3 positive 1. I can rewrite it as negative 5 times x raised to the power of negative 2 divided by negative 2. I can push this down. Two negatives will become positive. So this is 5 over 2 times x squared, right? 5 over 2 times x squared, positive arbitrary constant c. So this is what I have got. Now the solution. So let me just probably I can use this space because all I need is to write the solution. So as I mentioned to you, the solution is going to be z times integrating factor is equal to integral q times e raised to the power of integral p dx times dx positive c. Now I have found this value, right? I have found this value to be as 5 over 2 x squared. So I need to substitute that. So it's going to be 5 over 2 x squared comes in the denominator. So I'm taking it to the numerator. That's going to be minus 2. Okay. Positive arbitrary constancy. Now z, I have taken z to be as, let me show that to you. What is the value of z? I have taken z to be as y raised to the power of negative 5. So I substitute here y raised to the power of negative 5. My integrating factor that we have obtained is x raised to the power of negative 5. So this is the integrating factor. So I need to substitute x raised to the power of negative 5 there. So that is the solution. Probably you can, if you want, and then if you were to cross multiply, probably I can just show that to you. If you were to cross multiply, this is going to be 1 is equal to 5 over 2 times x raised to the power of negative 2 positive c times x raised to the power of 5 times y raised to the power of 5. So this would be the solution for this. So it depends on what you want and what you like. In fact, you can still simplify this. If you're interested, you can just push this inside. So if you were to push it inside, this is going to be 5 over 2 x raised to the power of 2 times x raised to the power of 5. That will be x cubed times y raised to the power of 5 positive t c times x raised to the power of 5 y raised to the power of 5. Of course, on the left hand side you got a 1. So this is a solution. Of course, having said that, what is your requirement? Based on that you can handle it. Students, we are given this question: dx over dy negative y times x is equal to y cubed x squared. Now, foremost, to solve this, what I wish to do is I would like to divide by x squared throughout. Now when I do that, I get 1 over x squared dx over dy negative yx divided by x squared is equal to yx cubed x squared divided by x squared. Now clearly we can cancel the x squared and the x squared. We can cancel a x and the x here, so this can be rewritten as x raised to the power of negative 2 dx over dy negative y over x is equal to y cubed. Now what I wish to do is I would like to make a substitution. So that substitution would be as follows. So before that, I would rewrite this as x raised to the power of negative 2 dx over dy negative y times x raised to the power of negative 1 is equal to y cubed. So I'm going to say let x raised to the power of negative 1 be equal to z. I need dx over dy. So if I were to differentiate, let me write that down. Differentiating with respect to y, so it's going to be negative 1 times x raised to the power of negative 2 times the differentiation of x is going to be with reference to y, dx over dy. This is going to be dz over dy. I can rewrite this as x raised to the power of negative 2 dx over dy is equal to negative dz over dy. So this is what I have got, and I can now take this and make the substitution. So what I would do is I would just take this as 2 and rewrite this. So therefore I can rewrite 2 to be as, in place of x raised to the power of negative 2 dx over dy, I would be substituting negative dz over dy followed by negative y times, in place of x power minus 1, this is going to be z, and that's going to be y cubed. Now I can rewrite this by multiplying throughout by negative 1. So if I do that, this is going to be dz over dy positive y times z is equal to negative y raised to the power of 3. So this is what I've got. So now what I can do is I can make from here, this is a linear differential equation, so we need to find the integrating factor and then solve it. So the integrating factor for this, usually we write integrating factor e raised to the power of integral p dx, right? But this time is going to be p dy. So that is going to be e raised to the power of, now whatever we got with z, that would be the value for p. So it's going to be y times dy, which is e raised to the power of y squared over 2. So this is what we have got. And now we consider integral q times e raised to the power of integral p dy times dy. So this is going to be integral, my q is y cubed e raised to the power of y squared over 2 times dy. This is what I've got. So now we need to make a substitution. So what is a substitution? I will just say let now there is a presence of a negative sign, so I need to place that. Now before I could make a substitution, I would like to rewrite this as negative integral y squared times e raised to the power of y squared over 2 times y times dy, and then I will take a substitution as 1 over 2 times y squared is equal to some t, and this is going to be 2 times y dy over 2 is equal to dt. So clearly I can cancel 2 and therefore I get y dy is equal to dt. I can make that substitution. So this is equal to negative integral y squared is 2 times t, and then e raised to the power of y squared over 2, that's going to be t. Y dy is dt. Actually the 2 alone is getting cancelled, okay, y stays there. So this is fair enough. Now I would like to use integration by parts, so I'm going to apply Liet. If I were to apply Liet, my u is t, my dv is e raised to the power of t dt, my du is dt, my v is e raised to the power of t. So using the concept uv negative integral v du, so if I were to use that, then I would have u is t, my v is e raised to the power of t, negative my v is e raised to the power of t, my du is dt. So if I were to integrate this, this is negative t times e raised to the power of t, positive integral of e power t is e power t, but my t, I can make the substitution back. My t is y squared over 2, so this is going to be y squared over 2 times e raised to the power of y squared over 2 positive e raised to the power of y squared over 2. So all these things are nothing but integral q times e raised to the power of integral p dy times dy. So this is what we have got. Okay, so now solution. So maybe probably I can use this base over here. So therefore the solution, so when you're writing the solution, it should be z times e raised to the power of integral p dy is equal to integral q times e raised to the power of integral p dy times dy, positive arbitrary constant c. So this is z times e raised to the power of integral p dy. This is what we have got, e raised to the power of y squared. So we can substitute e raised to the power of y squared over 2 is equal to, for this we have already got this, so it's going to be negative y squared over 2 times e raised to the power of y squared over 2 positive e raised to the power of y squared over 2 positive arbitrary constant c. Now we need to take into account the presence of a 2. Probably we missed that 2 there. So if I were to place that 2 inside, so this is negative 2. If I were to place that 2, so that would mean this 2 would get removed. So probably I will place one step. So this is equal to negative y squared e raised to the power of y squared over 2 positive 2 times e raised to the power of y squared over 2. So we will have to multiply this entire thing by 2. So this is have to be rewritten. So let me just get rid of this, and I need to substitute this. So this is z raised to the power of e raised to the power of y squared over 2 is equal to, I can take e raised to the power of y squared over 2 out, and if I were to do that, this is going to be 2 negative y squared positive arbitrary constant c. But we need to make some substitution for z, since z is equal to x raised to the power of negative 1. I need to substitute that. So it's going to be x raised to the power of negative 1 e raised to the power of y squared over 2 is equal to e raised to the power of y squared over 2 times 2 negative y squared positive arbitrary constant c. So based on your requirement, you can stop here, or if you wanted to go further, you can go further by getting rid of this. So if you were to divide by this quantity e raised to the power of y squared over 2, this will get cancelled, but the term will appear over here, right? So you can do that. So you can just say 1 over x is equal to, these two terms gets cancelled, so this is going to be 2 negative y squared positive, you're dividing, so it's going to be c times e raised to the power of negative y squared over 2. So I think this is the right place for us to stop. Students, we are given this question: solve dy over dx positive x times sine 2y is equal to x cubed cos squared y. Now I would like to have the right hand side and component over here to be a function of x alone. So to achieve that, I would have to divide by cos squared y both sides. So if I do that, this is going to be 1 over cos squared y dy over dx positive x times sine 2y divided by cos squared y is equal to x cubed times cos squared y divided by cos squared y. So clearly I can cancel this. Now 1 over cos squared y is secant squared y. So if I were to take this as 2, therefore I can rewrite 2 as secant squared y dy over dx positive sine 2y. Now what is sine 2y? Sine 2a is 2 times sine a cos a. Right? We know this formula. So this is 2 times sine y times cos y divided by cos squared y is equal to x cubed. Now I can cancel and rewrite this as secant squared y dy over dx positive 2 times x sine y divided by cos y is equal to x cubed. Now this is rewritten as secant squared y dy over dx positive 2 times x times tan y is equal to x cubed. So this is what we have got. Now in this case, the quantity that we will have to consider is 2 times tan y. So that is important. So foremost, what I would do is I will just make the following substitution. Let z be equal to tan y, and differentiating with respect to x, we get, so what do we get? Differentiation, this is dz over dx is equal to differential of tan y is secant squared y times dy over dx. So if I were to take this as 3, therefore I can rewrite 3 to be as dz over dx positive tan y, so it's going to be 2 times xz is equal to x to the power of 3. So this is what I've got. Now we will have to get the integrating factor. So therefore integrating factor is e raised to the power of integral p dx, which is e raised to the power of integral 2 times x dx, which is e raised to the power of 2 times x squared over 2. 2 gets cancelled, giving you e raised to the power of x squared. So this is what we have got as our integrating factor. Now we will consider integral q times e raised to the power of integral p dx times dx, which is integral, my q is x to the power of 3, so you can place that. My e is in fact integrating factor is e raised to the power of x squared times dx. So this is what I've got. So now we will have to use some techniques to obtain the solution. So we can do that. Now to integrate this, what I wish to do is I'm going to rewrite this as integral x squared times e raised to the power of x squared times x into dx, because x squared times x will give me x cubed. Now with regard to the substitution, I'm going to say let x squared be equal to t. This is the substitution that I'm going to use. Now with this substitution you get 2x dx is equal to dt. So this is going to be in place of e raised to the power of x squared is going to be t in place of x dx. So this is going to be x dx is equal to dt over 2. So dt over 2 I can substitute, but there is x squared here. Now I can substitute that. So this is what we are going to have, e raised to the power of t times dt. So I take u to be as t and dv is e raised to the power of t dt. From here I get du is dt. From here I get v is e raised to the power of t. This is integration by parts. So this is equal to 1 over 2 times uv negative integral v du. So this is 1 over 2 times my u is t, my v is e power t, my v is e raised to the power of t times du is dt. This is what I've got. This is 1 over 2 times t e raised to the power of t negative e raised to the power of t, which can be rewritten as e raised to the power of t minus 1. Of course the 2 is over there, but my t is x squared, so this is going to be e raised to the power of x squared over 2 times x squared negative 1. This is my integral q times e raised to the power of integral p dx times dx. This is what I have got. Okay, therefore the solution, let me use this space here. So therefore the solution, you have to understand, this is the Leibniz linear equation in Z. So the solution is going to be Z times e raised to the power of integral p dx is equal to integral q times e raised to the power of integral p dx times dx positive c. My Z is taken to be as tan y. So I'm going to say tan y, tan y e raised to the power of integral p dx. So that is going to be over here, e raised to the power of x squared. So I can substitute e raised to the power of x squared is equal to this entire quantity is this. So it's going to be e raised to the power of x squared over 2 times x squared negative 1 positive c. So this is what I have got. Now you can either stop here or you can push forward. Right, push forward in the sense you can get rid of this. You can say this is tan y is equal to x squared negative 1 positive. If this comes, is going to be c times e raised to the power of negative x squared. So this is a good place to stop for this question, students. We'll move on to the next one. Students, we are given this question, dz over dx positive z over x times log z is equal to z over x times log z raised to the power of 2. So foremost, to start off, what we will do is divide by z both sides. So if I were to do this, this is going to give me 1 over z times dz over dx positive 1 over x times log z is equal to log z raised to the power of 2 times 1 over x. So this is what I've got. Now I need to bring this into the Leibniz linear differential equation type of form. So for that I'm going to say let log of z be equal to t. So if I were to differentiate this with respect to x, we get, so this is going to be 1 over z times dz over dx is equal to dt over dx. This is what I've got. Now what I will do is I will have to substitute in place of 1 over z dz over dx as dt over dx. So this is the substitution that will be going in. dt over dx positive 1 over x times t is equal to 1 over x times t squared. Now what I will do is I will divide both sides by t squared. So this is give me 1 over t squared times dt over dx positive 1 over x times 1 over t is equal to 1 over x. So this is what we have achieved. Now what I'm going to do is I'm going to make another substitution. Why I'm going to make another substitution? Because this is a Bernoulli equation. Okay, so this being the Bernoulli equation, I would have to, in fact it gives me the privilege of making this substitution, which is 1 over t is equal to some v. Now if I were to differentiate this is going to give me negative 1 over t squared times dt over dx is equal to dv over dx. So if I were to take this as 2, therefore I can rewrite 2 as, the negative sign is not there, so we will have to push the negative sign here. So that would mean I get now dv over dx followed by positive. This is going to be v over x, right, because 1 over t is equal to v, which is equal to 1 over x. Now we can get rid of the negative signs by multiplying by negative 1 throughout. So if I do that, I get dv over dx negative v over x is equal to negative 1 over x. So this is what I've got. So now we will have to obtain the integrating factor. Now clearly you can see this is a function of x, this is a function of x. So the integrating factor is e raised to the power of integral p dx, which is equal to e raised to the power of integral negative 1 over x. So I can write it like this, which is e raised to the power of negative ln x, which is nothing but e raised to the power of ln of x power negative 1, which is going to be 1 over x. So this is my IF. Probably I can box this. So having obtained the IF, I need to obtain the q. Okay, therefore my integral q times e raised to the power of integral p dx is equal to integral, this is going to be negative 1 over x times 1 over x times dx, which is negative integral dx over x squared, which is integral x to the power of negative 2 times dx, which is, I can write this as x power negative 2 positive 1 divided by negative 2 positive 1, which is negative x power negative 1 divided by negative 1, which is negative 1 over x. Apparently there are two negatives here, so this will become positive, right? So this positive 1 over x, so I can write that. Now the final solution, okay, we have to start with the final solution as v times e raised to the power of integral p dx is equal to integral q times e raised to the power of integral p dx times dx positive c, which is v times e raised to the power of integral p dx is going to be 1 over x. So substitute that. That is equal to, this entire quantity has been obtained to be as 1 over x positive arbitrary constant c. Now you can rearrange it and then you can simplify this. So from here, if I were to cross multiply, I get v is equal to 1 positive c times x. This is what I've got, but my v is 1 over t, right? So if I were to take this as 4, so this would mean 4 can be rewritten as 1 over t is equal to 1 plus c times x. So from here I get 1 is equal to t positive c times t times x, but my t is log z. So if I were to take this as 5, then I can rewrite 5 to be as, probably I can use the space here, 1 is equal to log z positive c times log z. Of course there is a x there, probably I can place the x somewhere over here and place the constant c there. And this is a good place to stop. If you are not inclined to have the x, we can move this. In fact, if you are not interested to have this log x here, we can get rid of this log x, because it is with the constant term, we can get rid of it. So the best way to get rid of it is to divide both sides by log x. If I were to divide both sides by in fact log z, not log x, log z, then this would give me log z raised to the power of -1 is equal to 1 positive c times x. So this is a good place to stop, and that would be the solution to our question.